Okay, yesterday I think we stopped at this point. We said that we can map actually some part of our virtual address space to the disk, which is called mapped files. The advantage of this method is when you do this mapping using your regular assembly instructions, you may access your file data. You can read your files, you can write to your files, and your programs will not know if they are writing to the memory or the disk file. That's called the map files, and actually by doing so this becomes a very nice way of communicating with the other processes, maybe the processes on some other computers, if this file is shared over the network. Okay, so all the algorithms that I told you about inter-process communication, remember producer-consumer problems and etc. They were sharing some kind of data over the network, some shared place over the network. This can be done using these map files, and these map files can reside on this disk, and the disk could be a network disk. So basically you are doing this inter-process communication between two computers over the network, one at the end of this world, at this end of the world, and the other one is at the end of the other world, at the other end of the world. Okay, so that's the advantage of the map files. The cleaning policy, we talked about the demand paging. Demand paging says that, okay, don't allocate pages before the demand occurs, okay. But when the time comes for cleaning, we don't wait until we use up the whole memory, okay. This cleaning policy says that I will keep always 20-30% of my memory available. All those pages are available to the process. As soon as they say that I need a new page, without doing any page replacement, I get a new page. Okay. So when do we do the page replacement? Then there is a paging daemon. Okay. It's a process. It's an operating system process. It sleeps most of the time, but whenever the operating system realizes that we are running out of the free pages, virtual pages, then this daemon is waken up, and this daemon scans all the pages, and if you are using the working set algorithm for each process, it says that these pages are old enough that I am going to discard them, or maybe I am going to write to the disk. If they are modified, if they are not modified, I am going to just discard them. So we don't wait with this policy. We don't wait until we use up all the pages. Okay. So that I showed you many times with the Unix implementation or the Windows implementation. This is the algorithm we are doing actually. Okay. If two page frames are free, of course, it begins selecting pages to replace, evict, using some page replacement algorithm. But again, if you have too few pages available or free, that means that you are running into problems. You will most probably trashing. Okay, you will most probably trashing. This means that, okay, if you have just a few pages available, that means that this paging daemon couldn't find any pages to discard when it runs. That means that everything in my memory is in the working set. If I get rid of some of the working set pages, then that means that I am going to load them back again so that the process can run, and that will cause trashing. Okay. So that's one cleaning policy demand paging uses. Good. So with the operating systems, when does the operating system get involved with the paging? During the regular runtime, when we are, remember, the CPU produces an virtual address. That virtual address is automatically translated into physical address, and that's done by the hardware. That's done by the MMU. So during the regular runtime, when you access your memory locations, whether they are instructions or data, everything is handled by the hardware. Operating system is not involved at all. So when does the operating system get involved? Okay, first at the process creation time, of course, for each process you need to set up a page table, okay, and you need to start allocating some pages for that process. That's one thing, okay. During the process execution time, whenever the context switch happens, of course, you need to save the process page table, and you need to load that back again. You need to reset the MMU. You need to flush the TLB so that you don't carry any data from one process to another process. That happens during the program execution time when the context switches happen. Okay. And when the page fault occurs, remember, page fault is an interrupt, hardware interrupt. It happens, okay, it is created by the MMU. MMU says that I am going to translate a virtual page address, I am going to translate a virtual address to a physical address. But I don't have the page number. I don't see it in my page table. So I am going to create an interrupt. And this interrupt will be handled by the operating system. That interrupt is called page fault interrupt, or page fault simply. Okay? So when the page fault happens, operating system has to take care of it. It will find the page number, it will find the available pages, and it will do the replacement according to the algorithm that we are running. And of course, finally, when the process is terminated, we have to release all the pages. We have to clean up all the mess that we have created for this process. So that's the process termination time. 4 things that the operating system is involved with the paging. Most of the time, operating system doesn't do anything, because most of the time what we are doing with the paging is translating virtual addresses to physical addresses. That's done automatically by the MMU. But somebody has to program the MMU. That programming MMU is done during the creation time, context switching, page fault, and the process termination time. Okay, so that's operating system and paging. Good. So what did I say again? Page faults are actually interrupts. So somebody has to handle the interrupts. So how do we handle these interrupts? Let's look at the steps of handling a page fault interrupt. And these steps will be very similar to what we have seen before, actually. Remember, we have seen the steps of handling an interrupt. This will be almost the same thing, but we know this time the interrupt type. So this will be a little bit more detailed maybe. So the hardware traps to the kernel when the page fault happens. By hardware I mean MMU, okay? MMU creates the interrupt, and the effect of the interrupt is hardware trapping to the kernel. Now I am in the kernel mode, and I will start immediately doing whatever the regular interrupts does, okay? So I save the program counter on the stack. I need to save it. I need to remember where I have left, okay? And then the assembly code of the operating system starts running. It starts saving general registers, okay? Not all of them, just enough number of them so that I can continue running operating system procedures. You don't want to save everything, because that's maybe some waste of time. Maybe operating system will not use all of those registers. Okay, then our operating system page fault handling procedure starts running after that, okay? So these are exactly the same steps that we have seen when we handled the interrupts before, okay? Now, I know that it's an interrupt for the page fault, okay? And the operating system tries to find which virtual page needed, because MMU says that I have a problem here. I cannot find the page frame number for this virtual address. So operating system tries to discover from the MMU and from the code what page is needed and what page is not in the page table in the MMU. Okay, I have discovered that. Okay, I found it, and then I check if that address is valid. Okay, so am I trying to access an invalid virtual address? Okay, or am I trying to access an virtual address that is not with the right privilege? Maybe that address is read only. Maybe I cannot execute that address. Okay, so I am checking that. If that happens, if I see that that address is not valid or there is a protection problem, then operating system enters a mode that say that there is a segmentation fault or there is a access privilege problem, etc. Usually that results in the termination of the process causing this problem. Okay. If I know that the address I am trying to access is not invalid, then I will continue. I know the address. Okay. Then I need to do maybe some page replacement. I mean, this doesn't happen all the time. Okay. I don't have to select a page that needs to be replaced, okay? Because what did I say before? With the demand paging, there is always some free pages available. So you basically just choose that free page without doing any replacement, and you load your data from the disk to that free page. But in this case, it assumes that you are doing the page replacement. If the page that I have selected, okay, is dirty, then I schedule my operating system procedures to transfer to that page to the disk. Okay, that's going to take a while. Then at this point, operating system cannot continue anymore because I need to wait until that page is written to the disk. So the original process that caused the interrupt, page fault, will be suspended. Okay, that's the assumption. For some of the algorithms, remember, we don't do that. If we select a page that is modified, we schedule for the transfer to the disk, and we try to select some other page so that we don't get suspended. Right? That might be another algorithm. Okay, so as soon as the frame is clean, so what did I say again? Most of the time we don't do this number 5 with the demand paging, because the page that we select is already clean, because demand paging makes only 20% of the, keeps 30% of the pages available. Okay, as soon as the frame is clean, okay, operating system looks up the disk address where the needed page is. Okay. This doesn't happen this way always, because that page might be in the memory. Okay, how could this happen? MMU says that this page, I can't find this page in my table, but I see that that page is in the memory. How could this happen? MMU says that I couldn't find this in my page table, but the operating system says that, well, that page is in the memory. Can you explain this? How, or maybe is this impossible? But I'm saying that no, it is possible. It could happen.
Maybe another process's page table.
Maybe another process has this page in its page table. That's one explanation. That's why I don't have it in my page table, but some other process has it. Or it is in my page table, but it is not in MMU's TLB. Remember, MMU is a small place. It can't hold all the page table information. Page table is very, very large. Sometimes it is much larger than your total amount of memory, right? You can't fit the whole page table in MMU. So inside my MMU, there is only TLB, okay? Look ahead buffer. If it is not in TLB, then I will get a I will get a page fault, okay, and I will have to handle that thing myself as the operating system. Okay, so when I get the clean page, then I need to load it from the disk, assuming that the page is not in the memory. So that means that I need to wait. There is no escape from the step. Okay, somebody has to load that page from the disk. So my process will be suspended. There are ways of avoiding this step number 5 with the demand paging. But if the page that I am going to load is not available on my memory, then I will have to unfortunately wait until that page is available. So that will suspend my process for a while. Okay. So how do we do the loading of the pages again with the help of the interrupts? I programmed my DMA, or I asked my driver to load that page, and the control is loading those pages, and I am doing something else with some other process. When that page is available, of course, the disk controller will cause an interrupt. Will say that, okay, the page that you are trying to load is ready now. Okay, now I have to handle that interrupt myself. Okay, so that's another interrupt handling that will go back to the top of this interrupt handling routines and etc. Assume that I have done all of those. When that page is ready, operating system realizes that whoever is waiting for this page can be waken up. It wakes me up. Okay, operating system is waking up some other operating system routine saying that this page is ready. Okay, and when that page is ready, of course I have to update my tables on my main memory, also the MMU2, okay, and then now the time comes back to the original process causing this page fault to start again. But there is a procedure of instruction backup, and we will see. Instructions are not just single bytes, right? Some instructions are large. They include 2-3 parameters. Okay, each of those parameters could cause the page fault. Okay, maybe I will find one of the parameters but not the other two. Maybe 2 of them are available, etc. So I need to back up that instruction. I have to. I did execute some part of it. So I need to back up that instruction so that I am starting from the beginning. Now I can continue and finish up with the rest of the instruction execution. Okay, and I do the backing up, and that process can now continue its execution. Okay, so the execution doesn't start automatically. Execution, I will be put on the ready queue. When the scheduler lets me run, I will run. I will reload my register and other state information, etc. When the scheduler lets me run again. So that's what happens. Actually, we have seen many of these states when we handled the interrupts before, but only the thing is that actually we have seen this one too. Remember this one? When the interrupt happens, I am in the middle of an instruction execution. Most of the time, this is simple, but with the pipelined systems, I mean, it is very difficult to know where I am exactly in terms of execution of many instructions at the same time with the pipeline structures. So it was difficult. So the same problem here again. So what else? Okay, here. These 2 things, page replacement could be done maybe during the page fault handling, or setting up all the TLB tables, and setting up of the TLB tables and page tables and etc. They are all specific to page fault handling interrupts. But basically, it's a interrupt handling routine. Okay, if you look up go back to the chapter number 2 and look at how we handle the interrupts, the steps of it, you will see that it is very, very similar. It is very, very similar. It's all parallel. Okay, any questions about page fault handling? Yes?
Is there any page fault which cannot handle by operating system or hardware?
Well, that must be a page that is not available. You can't access that page. That address is not available, and etc. That's called segmentation fault or invalid address fault. So, well, if there is such a thing, that means that memory is not available. What am I going to do? So I will terminate the process, or I will let the process that you cause such a problem. I mean, if the address is a valid thing, then there is no way that the operating system cannot handle. I mean, do you have any ideas of when such a thing can happen? Do you have any ideas of?
Could you repeat it?
Do you have any ideas of when such a thing can happen? The operating system can't handle the page fault?
Crash.
What? Crash already means that. Oh, you mean that after a crash, you are trying to. I mean, somebody is executing nonsense instructions, and those nonsense instructions are causing page faults, and those pages are not available already. So that will cause this one. I don't know that address. I can't access that address. You don't have the privilege to access that address. So you are going to get, for example, when you try to say, give me the address number, okay, write 5 to the address number 0000. There is no such thing as 000. It is always reserved, okay? So page table will not have any entries for that virtual address. And you cannot load that address from the disk. It is not available. So that's an automatic segmentation fault, okay? So usually the crashing programs will cause these kind of stupid errors. Okay. Well, crashing program doesn't mean that it is automatically terminated. It is doing something nonsense. When you do lots of many nonsense things, some of them will cause this problem, segmentation faults, invalid address accesses. Okay. Any other questions? Yes.
When a page fault is occurred, the first step is to look for in TLBs, right? The second one?
No. The TLB is automatically handled by MMU. MMU always, when the virtual address comes to me, okay, I look it up in my TLB. If it is in TLB, then I handle everything, okay? If it is not inside the TLB, then I will cause this page fault.
Yes. So the searching for the lost pages, is it not possible to find it in the memory? I mean, we have to go directly to the hard drive.
No. Well, that's what we said as the number for the number 6. If it is not inside the TLB, it could be still in our memory.
Yeah.
Okay, that's not. Remember, that's called soft miss, not hard miss, but soft miss. Okay, it is not in the memory, but it is in the. Can I find it? Let me not forget about this one. So this is page number 100. When we talk about the way before the page replacement algorithms, yeah. So the soft miss is when the page reference is not in the TLB, but it is in the memory. Okay, it is still a page fault because operating system has handled it, but relatively this is cheaper. Okay, it is still not as fast as TLB handling everything, but this is better than going to the hard drive. Hard miss is when the page itself is not in the memory. Okay, both of them are page faults, but soft misses are much faster to handle. Okay, so sometimes we call them a minor page fault or a major page fault. soft miss, hard miss, minor page fault, major page fault. Okay, and the segmentation fault, the program simply accesses an invalid address. These are the terminologies. Okay, so I did that. Any other questions on this one? Let's look at this instruction backup. See this one, instruction backup number 6. Okay. Let's look at this instruction. Instruction says that, okay, move the address shown by this register A0 to address shown by this register A1. So what does that mean? Indirect accessing. Okay. First of all, I need to reach 2, 3, 1, 2, 3 memory locations. Okay. When I reach this address 1000, it may not be in the TLB. Okay. This one may cause an page fault, or this one, or this one. Or when I say that, okay, I am going to load this memory location into, okay, with the indirect addressing, what do? You get the address of the memory from your register, you go to that memory, you get that value, and I am going to put this to this memory location. So a simple instruction can cause 5 different memory lookups. Okay, so there are 5 possibilities out of this instruction to cause the page faults. Somebody has to remember this, okay? Which one has caused it? And somebody has to remember what part of this instruction I executed already, okay? And when the page fault is handled, okay, then I need to back up the instruction so that I am starting from the fresh. I didn't load that data from the memory yet. I am starting from the beginning and I am executing this instruction. Exactly the same problem that we had with the interrupts when they happened before in chapter number 2 with the processes. Okay, so there is nothing much special about page fault handling about this instruction backup. We have to do this for any interrupts anyway. Again, as I said before, this gets much complicated when we have a pipeline system, because we are not executing a simple instruction at the same time. We are executing many instructions at different phases because of the pipeline structure, and instruction backup becomes more involved in that case. Okay, another interesting thing, well, I mean, when we introduce ideas with the paging seems very simple. Actually, it is simple, and it seems that it solved many problems, but with these kind of ideas, many problems can occur, and some of them rarely occur, but they may cause some nasty problems. One of them is this problem, okay? Suppose I have a process, it starts an I/O read, and then it blocks because I cannot continue without reading those data from the disk, okay? And since I am waiting, I asked the operating system to load some data to my buffer, okay? My buffer is in the memory. I am waiting for that buffer to be filled in. I am suspended. Since I am suspended, some other process is running, and that process needs new pages, and the operating system decides that it can replace my buffer. If the buffer is replaced, and if my data is ready, where does the operating system put my newly loaded data? Because it is my buffer is replaced. Okay, so I mean, most of the time when I'm waiting for something to happen, I am suspended, and the operating system might think that this buffer is not used for a while, or least frequently used algorithm, or least recently used algorithm might decide that I can replace this one. And if it is replaced, then the operating system cannot put my data into the required buffer. So that's a problem. To prevent this, okay, there is a way of locking or pinning the pages, okay? Operating system, well, as an ordinary user, I can't do that because that's too much privilege for me. But the operating system says that this page, okay, it will stay in the memory. You will not replace it. Okay, that's called locking the pages. Okay, that's called locking the pages. This will not be replaced. And another alternative is using the kernel buffers. It's like this is my operating system. Okay, this is my regular process P1. I am asking the operating system to load my data to this buffer, and this is my kernel, and this is the hardware. Okay, with this approach with the buffers, you load your data from hardware to the operating system kernel buffer, and when that data is available now, I can start running again as process number 1. I can copy this data to my buffer. So kernel buffers is a solution to this problem, or locking pages in memory is something that we can do. Of course, when you start locking stuff, I am locking this page, and when you lock many things at the same time, you may run into some deadlock problems, because I locked this page, I locked the other page, but I can't lock this page because something else is happening, and that means what? That means there is a potential for deadlocks, and we need to be careful about this. Okay. Good. So that's one issue. Again, these are all issues in virtual memory designs. Somebody has to solve all these problems. Somebody has to see all these problems. Important problems. Some of them are very, very involved. I am just giving their names and giving the definitions, and most of the time we are not giving the details of the solutions. We are just introducing the ideas. Okay, we talked about this stuff. We said that we write that page to the disk, we load it from the disk, and etc. We keep talking about writing to the disk and loading from the disk, but we never talked about where do I write those pages on the disk. Okay, where do those pages live? Okay, so that's called the backing store. Backing store is the place where you save your pages, unused pages, okay, on your desk. Okay, that's called the backing store. Where do we store the pages on desk? So remember what we said. The Intel architecture, 32-bit computers can address 2 to the 48 bytes of virtual space. How much space is this? This is kilobyte, megabyte, gigabyte, terabyte. Okay, so it is 250,000 terabytes of space, right? It's something like that. Okay, 250 terabytes. Is it gigabytes? Is giga? Kilobyte, megabyte, gigabyte, okay, terabyte, it's a terabyte. Okay, 256,000 terabytes of virtual address space. I know that I don't have that kind of physical memory. All I have is 8 gigabytes, 16 gigabytes, 64 gigabytes, and etc. So I know that this can't be fed into my physical memory. But how about your disk? Do I have these kind of disks? Yeah, well, nowadays, yes. But I am talking about this one. I am talking about 2005 or maybe 1998. During those days, the Intel architecture was able to support these kind of virtual addresses. So these kind of disks did not exist at those times. Even today, if I try to write all this virtual memory to my disk, okay, and remember, I need to keep this data for each process. Okay, each process needs this kind of a data, and I am talking about hundreds of processes running at the same time on my computer, now this is not manageable. I mean, you don't keep all of your data on the desk. We don't have that kind of a desk. Okay? But the nice thing is that no process is this large. No process needs this kind of virtual memory. Most of the virtual memory that I can address is empty. I don't have to keep them. So if your idea is keep all this data on your desk, and if the address is empty, just keep it empty, is not a good idea. Okay. So the simplest algorithm is to have a special swap partition on the desk. So try to keep exact copy of the virtual address on your desk. It is wasted this space. Okay. So that will be the thing. Okay. So my page table is a very large page table. I can have 2 to the, let's say 2 to the 48 is my virtual address space. If I have 2 to the 12, 2 to the 12 page sizes, 4 kilobyte page sizes, then in my page table I will have 2 to the 36 entries, and most of those entries will be empty, I know. But if the entry is empty, then I just keep a pointer to my swap area on the desk. Okay. So this swap area is actually exact copy of my virtual address space. It's a very, very large space, and most of the time, most of it is empty. So I have only 4 pages available on my memory. Rest of them will have to stay on the desk. But as I said, many of them will not be used. So the idea is this. Why are you keeping all those unused places? Okay. The idea is this. Okay. There is a disk map. In your virtual memory, keep the list of used pages and keep a pointer to those pages on your swap area on the desk. There is a special swap area on your desk. Usually it is the most convenient, for example, easiest to access area on your desk. And I keep my swapped pages on that area. That's called the swap area on your desk. That swap area is your backing store. Okay. So allocate this space for each page when it is swapped out. Otherwise, don't allocate any space. Don't try to keep all this kind of data on your desk. That will be too big. Even for today's computers, that will be too big. Okay, good. Any questions? Backing store is important. Usually when you set up your operating systems, either Linux or Windows, you usually have a parameter asked by the operating system. Linux, for example, when you set up a Linux operating system, when you install a Linux operating system, it will first ask you how large a swap area do you want. Okay, you say that, okay, I need 1 or 2 or 10 or 90, 64 gigabytes of space or 1 terabyte of space. So I'm going to keep maybe 10% of my whole disk as swap area. Okay. Of course, larger the swap area, better for the operating system to make those decisions. But keeping it too large doesn't give you any help. Okay. So backing store, that's the definition, and 2 alternative approaches. Nobody uses this one. This is too wasteful. This is the way to go. Okay. You only swap out to the disk when the page is swapped out. You don't allocate your pages on the disk before the process starts. Okay. Any questions? So after each 5 minutes, I am introducing an important idea. I am telling you about that. Define the problem, give you some solutions. None of them are detailed. None of them are to the exact point. But the idea of this end of this chapter is to give you these kind of complications. I mean, there are many complications about this kind of I mean, memory handling of the memory is very detailed thing. It's not easy. Okay, let me continue then. We talked about this topic, separation of policy and mechanism before. Okay. Before talking about this, let's look at this example. We talked about many things about memory management, okay? And all of these has to be done by the operating system. We are talking about the paging daemon. We are talking about the cleaning policy, page replacement algorithms. Some of them are complicated. We are talking about where do I store all that information on the disk and etc. These are all complicated stuff. You can't write like 100 lines of code to handle all of them. That means what? That means I have to make my kernel larger, right? Lots of code, lots of possibility is something to go wrong, okay? Some people said this, why don't we do this, okay? I mean, yes, I mean, to handle the memory, I need special privileges. For example, to read the R and M bits from the page table, or set up the page table, or set up the TLB, I need kernel privileges. I can't escape from this. But if I keep the main logic of the page replacement, or the cleaning policy, or the page table setup, in some procedure that lives in the user space, my operating system has a user process. That user process makes all those calculations about which page is going to be replaced, where it is going to be stored, and etc. So the main thing, main policy, page replacement policy, backing up policy, what else? The swapping policy, everything, all the logic, all the brains of the page replacement stays in the user space. It does all the swapping out and loading of the files and everything, or loading of the pages and everything in the user space. Whenever the data is ready, it just lets the operating system know that, okay, this page is ready. You can set up your TLB buffers or the page tables. Okay? So this is the mechanism part. This mechanism part actually doesn't know what it is doing. This part knows what it is doing. Okay? So the brains of the whole system lives in the user space. So this is the more complicated part. This one will take tens of thousands of lines of code, but this part is simple. It just does whatever it is told so, okay? It just modifies the R and M bits and that kind of stuff. So the code is here simple, very simple. If I made a mistake, the possibilities of making a mistake here is much less than possibilities of making stupid mistakes in there, because it's a much larger code. So the nice thing is, I am keeping my kernel small. Small kernel means that less chances of having a bug in my kernel. Okay? That's why people enforce this idea of let's separate the policy from the mechanism. Policy is large. It is complicated. It knows what it is doing. Mechanism is something simple. It just modify this bit and this bit, and put this page at this address, and flush the TLB, and those kind of simple instructions one after the other one. Okay, this is just a monkey, very reliable monkey. Okay, doing whatever it is told to so, and it can't do more than that. But this is the one that has the logic of it, that has the brain of the whole thing. That's called the separation of the policy and mechanism, and we try to apply this idea to all the parts of the operating system. Try to keep your logic, okay, main algorithms in the user space, Of course, this external pager doesn't have any privilege to access the MMU tables, TLB tables, interrupts, and etc. It only says that your data is ready. I did that, okay? So I'm saying that, okay, I'm going to replace this page with this one, and I've loaded all that done from the disk, and I did everything. All you are going to do is just replace this with this one. Okay? So we do this with the paging. We can do this with the scheduling too. Okay? Run your scheduling algorithm in the user space. This is an operating system process, but it's not a privileged operating system process. Okay, it's an operating system. It is protected, of course. There is a protection between these two. Of course, there is a protection. I mean, nobody else other than the operating system knows what's going on inside that. It is protected, but again, this is not in the kernel space. The other nice thing is about this one is not kernel dependent. I can take this external pager, okay, and I can move it to some other operating system. Take the external pager of the Windows operating system, put it on top of the Linux operating system, and with some small modifications, it will start running. So this is kind of operating system independent, hardware independent, kernel independent code. That's another nice thing about this one. Okay, suppose you have changed your CPU, you have a new MMU, okay, you have a new TLB structure, your external pager will not care about it. That's the other nice thing. Okay, so let me go back and let me try to go over these items one by one, but I think I am out of time for now. Let me stop at this point. Let's be here around 11:34. Yeah, 11:34. 10 minutes. Where is my attendance? Herkes imzaladı mı arkadaşlar bu şeyi? Yoklamayı.
Belli de olmaz mı? Biraz daha yapıyoruz ama. Diyeceğim hani bir kere gazlanmıştı böyle bilmem ne çok alakası yok. Şöyle 15 dakika falan güzel.
Nereden bileyim diye veriyorum tabii ki ben de Nasıl bir dakika? Mesela beni yazdığı koda bak bakalım. Çünkü şeydir yani belki eliyle attıysa biz yakınları koyduk. Bir bakalım, bir bakalım. Şeye bir baksana ya, dokuzda arge tipine ne atıyor?
Joy vardı, olsun. İyi var. Onu yap.
Tamam.
Tabii nereden
Tamam. Hayır hayır hayır, biz oraya hiç dokunmadık. Burası mesela şimdi şeyleri atıyor. Kapıyı ben şu an ekranda bir şey göremiyorum. Dondu. Aslında da başmış yani. Kapı diye ekledim. Ama içeri atmıyordum acaba entegrasyonda diyorum. O kodu geçti mi böyle bir şekilde? Tamam. Tamam, bunu 9000'e attığı yer nerede? Yine mi dondu ya? Ah, çok sergide var ya, utansın kendinden ya. Bedava yine. İnternet bağlantısı bir şey yok hala. Toparladım.
Hayali var ya. Resmen falan. Bayağı iyi olmuş.
Hayır, kapıyı hiçbiri açmıyor işte. Sadece burada hiçbirinde kapı yok. Bir kontrol etmiş ama içeriye kapıyı almamış.
Şükrederiz bence. O da var. Şükredelim bence gerçekten. O şey en mükemmel. Bizim okulun mimarlığı mı olsun? Bir de bana bir diye bir şey yok.
Yalan mı?
Yani böyle 16'da geliyor.
Okay, using this idea of separation of policy and mechanism, we divide the memory management into three parts. One is the very low level MMU handler. Of course, this is machine dependent. It depends on the processor, and it is done in assembly code. It is this part of the operating system, MMU handler, machine dependent. The second part is again the part of the kernel is page fault handler. Somebody has to handle the page faults. Remember, the page faults are the interrupts. Somebody has to handle those, and again that's the machine independent, because whenever the interrupt happens, it finding the what instructions are causing this page fault, and doing that kind of stuff. Remember those 7 steps, 8 steps, is done in a machine independent way. Is the mechanism for paging. And then the main thing that runs in the user mode, user space, is the external pager. It is a policy. It is the machine independent part of the memory management. It is the part that is responsible for loading data, to writing data to the disk, and getting the data, and providing all the data for the fault handlers and everything. Okay, so since this one doesn't have privileges to play with the MMU, page tables, and etc., it has to do lots of system calls. System calls means context switching. Context switching means performance loss. That's the downside of this method, separation of policy and mechanism. If I have implemented everything in the kernel space, then I wouldn't have these kind of problems of communicating with the kernel, because I am the kernel already. That would be the case, but in this case, if you separate the policy and mechanism, you will run into the risk of, you will run into the risk of many switches to the kernel. But this structure, separation of policy and mechanism, is very modular, easier to manage, and it is less sensitive to the errors done in the pager. Okay, so that's about the separation of policy and mechanism. Any questions on this? Again, this is not specific to only memory management. In almost every part of the operating system, whether it says scheduling, is handling of the CPUs, or the file systems, and etc., we like to do this separation of policy from the mechanism. Good. So that kind of completes my discussion about this paging stuff. Paging is not the only way of achieving virtual memory. There is an alternative method. It's called segmentation. Okay? So segmentation is as old as paging. Nowadays, we don't use segmentation much. The Intel environment, in fact, it supports segmentation, but the latest Windows or the Linux operating systems, they don't use segmentation. They completely get rid of it. But I mean, we will never know. It may come back again, and it has some historical significance. Let's look at this segmentation, not paging, but the segmentation. Segmentation is the idea-wise, it is very simple. It is simpler than the paging, actually. And by itself, segmentation doesn't work very well. If you combine segmentation with the paging, it becomes very, very effective. Okay? So the idea is this. The virtual memory, the address space, is something one-dimensional. From address number 0 to address number FFFF, you can do whatever you want. They say that this is too simplistic. Okay? Remember the separation of the instruction space from the data space? That was good. Why don't we make this idea more generalized? Let's generalize this idea. Instead of having one-dimensional virtual addresses, okay, let's have many different virtual addresses. So for my process, there is this virtual address 1 space and this virtual address 2 space, virtual address 3 space. Their sizes are different, okay? At the beginning you say that, okay, I'm going to keep my procedures inside this V1, my code. I am going to have some need for a large data. I am going to keep my large data here. In V3, I am going to keep my specialized procedures, shared procedures. Then I am going to do this V4. It will have some kind of other special data. And each one will start from 0 to some number, 0 to some number, 0 to some number. Okay? So each segment has a purpose, and the programmer decides how many segments they are going to have, and the programmer decides which segment is going to be used for what. Okay? So previously with the paging, the programmer didn't know anything about the paging, right? The programmer knows about, for the paging, programmer says that I have a very large address space that starts from 0 to some very large number, okay? And I can do whatever I want inside this virtual address space. And under the hood, this virtual address space is divided into pages. There's paging in and paging out, and the page replacement, they are all happening without the knowledge of the programmer. In this case, programmer knows these pages, okay, and programmer specifically tells the operating system how many pages it needs, and it knows where the data lives inside these pages, okay. That's called segmentation. And I think the book gives this example. Let's say I am developing a compiler, okay, I'm making a compiler, okay. For the compiler to work, okay, I need to keep the source text, the program that I am compiling, in some segment. My symbol table, my variables, okay, their names and attributes, I am going to keep it in another segment. Okay, I will keep my constant in another table. I will keep my parse tree synthetic analysis results in another table, and another segment, sorry. And for the fifth segment, I am going to use it as a stack. Okay, so that's and these are all supported by the operating system and the hardware. Okay, and you ask the hardware to give you a segment, and it's going to give you a segment, and you don't care where the segments live. Okay, all you care is, okay, of course, I mean, there is no such thing as these segments are by themselves are physical memories. Of course, these are virtual memories, and it is the responsibility of the hardware and the operating system to put V1 here. For example, V2 could be here, okay, V1, V2, and V3 is here, and there is some space between these two, and maybe the rest of it is empty. Okay, it is the responsibility of the operating system, with the help of the hardware, to move these segments around in my memory. Okay, as a programmer, I don't know where my segments live in the memory. All I care is that each segment starts with address number 0 up to their sizes. Okay, so that's called the segmentation, and this is the same picture for that compiler. I have 1, 2, 3, 4, 5 segments, and it looks like this segment is full. This segment has some empty place. This one some empty place. Okay, so the compiler works this way. Compiler works this way. So when you write a compiler process, compiler program, you ask the operating system to give you 5 segments. You maybe specify the sizes of the segments, and later, if you like to grow some of your segments or shrink them, you can do so by asking the operating system. Okay. Again, the address translation happens automatically. Address translations happens automatically. when the program says that I am going to access the fifth element of segment number 0, for example this address will be automatically converted to the physical address by the MMU, okay, during the program execution. I don't know where the exact physical address is as a programmer. All I care is that segment number 0, the address inside the segment is this. Okay, that's called the segmentation. And the segmentation fault, the name segmentation fault comes from this picture actually. The name kind of stuck and we keep using it even though we don't use segmentation at all. Okay, segmentation fault means that you are trying to access it out of this segment, so it's a segmentation fault. Okay, so again, I have 1, 2, 3, 4, 5 segments, and the size of each one is different. And as a programmer, I have designed this. As a programmer, I asked 5 different segments from the operating system. Okay, again, the segment is a logical entity which the programmer is aware and uses as a logical entry. And the segment might contain a procedure or an array or a stack, or you know the idea. It is designed by the programmer. So programming in this kind of an environment is a little bit different than programming with the paging environment. Okay, so some of the advantages of, again, segmentation. Remember the DLL libraries with the paging? It was a nice example of using paging. We said that for the process number 1, this is the virtual address space of the process number 1 and the virtual address space of the process number 2. Process number 1 thinks that there is a library at this position inside the virtual address space, and the process number 2 thinks the same library is available at this position, but in fact these are just page tables pointing to some memory location in the physical address space. Okay, this way I am sharing the DLL libraries. Okay, we said that this is nice, but there was a problem with this issue. We have to be careful about what? We have to be careful about, if you are writing such a shared library that will be shared by many processes. Relocatable code. What did you say?
Race condition.
I-
Race condition.
Race condition?
Yes.
Well, I mean, race conditions are always problem with the shared memory. Yeah, we have to handle it. I'm going to have the shared. If you have a shared memory, then you will have the race conditions. But other than the race conditions, there is a special problem for one relocatable code or position independent code. If you, let's say, remember this one, the exact same problem. If there is an instruction that says that jump to address 40,000, okay, 40,000 inside this code, yes, I can jump to it. But if you issue the same thing, jump to 40,000, it will jump to some place around here. So what I'm saying is that you can't use absolute addresses inside these shared parts of the memory with the paging. It has to be position independent code. If I do the same thing with the segmentation, okay, if I do the same thing with the segmentation, let's say inside the segment, is not parse tree. Let's say this is my dynamically linked library. Everybody is, okay, all the programs that needs to use this dynamic link library, they share the segment number 3, and address is always 0 here. Okay, so this DLL has a special segment to it. This is a shared segment, and inside this segment all the addresses are, they look like physical addresses. I don't have this restriction of having to use position independent code. My code could be dependent on the position or inside the segment number 3. Okay? So this is a very nice advantage of the segmentation over the paging. Okay? So I think I was talking about this one, right? Yeah. So the linking of procedures compiled separate is greatly simplified. Okay? Every procedure knows where it is inside that segment. Linking simply means that you are going to use this segment and you are going to use this segment. That's it. With one-dimensional memory, okay, changing the procedure sizes will affect their starting addresses. So we will run into this problem of position-dependent code. So that's the main advantage of the segmentation. It makes these kind of writing shared code programs very easy. Also, logically, you get help from the hardware and the operating systems to support your needs. For example, you decided that you need larger source text segment. You ask the operating system make this segment larger, so it's going to get larger. How are you going to do this with the paging? Okay, paging starts from address number 0 to some large address, and if you like to keep your source text in some part of your virtual memory, and if you decide that you need some larger part of your virtual memory, you need to shift things up or down. So this is done automatically by the segmentation. Those are the advantages. So we don't live in a world where a solution is always better than the other solution. So what do you think that the problems of segmentations are? So we talked about the shading of segments, or shrinking or the growing of the segments. These are the advantages of segmentation. What is the disadvantage of the segmentation?
I think it's more complicated than this page goes. Page.
You mean, when you compare it to the paging, it is more complicated for the hardware. You mean,
No,
or for the
software.
you mean as a programmer?
Yes.
Well, I mean, if you don't like this idea, just use a simple, just one segment. Nobody will stop you from that. If you like the idea of linear address space, starting from 0 to some large number, then nobody will stop you there. Okay?
So why we call it as segmentation? Segmentation.
But you said that makes it complicated for the user. I mean, if you like to keep it simple, then use it that way, so you get the best of both worlds. But that's what I'm saying. No, that's not it. No, it is not complicated for the end user, but there is some serious problems with this one. Think about the hardware and the operating system. Where do I keep these segments? Let's look at this. Let's look at the segmentation. Okay. In my physical memory, this is the segment number 0, 1, 2, 3, 4. Okay. Since this is the physical memory, I am running out of physical memory. What do? If I need a new segment, okay, I need to swap out this segment and put this segment number 7 in there, right? So I have this 3K space now. And then if I need a new segment number 5, I got rid of segment number 4 and I put it in there. So what am I having in here? Okay, I will end up having this place empty, and this place empty. I have a total of 10 kilobytes available in my memory, but I can't have a contiguous segment of size 10K, right? So what is this problem? This problem is called fragmentation. Yeah. We didn't have the external fragmentation problem with the paging, right? But with the pure segmentation, there is an external fragmentation. You might say that you may say that, well, why don't you run a compaction algorithm from time to time? Yes, you could as an operating system. I can move things around and I can compact my memory, but that's going to take some CPU time, operating system time, and I don't like that. That's the problem with the segmentation. Problem with the segmentation. So in fact, implementation of pure segmentation is called pure segmentation. Okay, that's problematic. To solve this problem, okay, they invented this idea of segmentation with paging. Okay, segmentation with paging. Why don't I separate these segments into virtual pages, and for each segment use the same paging idea? Okay, so I can keep my pages anywhere in my main memory. I don't have to keep these pages contiguously. I can keep those pages in anywhere in my main memory, so I don't have any external fragmentation problem. I don't have any compaction problem. So segmentation with paging will solve these problems, and I will get the advantage of both paging algorithms and the paging systems and the segmentation systems. Okay, that's what they said about the segmentation. So most practical systems that does the segmentation, they use paging with the segmentation. And we are going to see the first one that use this idea, MULTICS, in a few minutes. Okay, let's try to compare these two ideas, segmentation and paging. This is directly from the book. Okay, so this is the paging column, segmentation column. For the segmentation, the programmer needs to know that it is running in a segmentation system. So the programmer be aware that the techniques is being used, yes, for the segmentation, because the programmer says that I need 5 segments. I'm going to give you the sizes of each segments. Okay. For the paging, the programmer doesn't know that there is a paging system running. Okay. And with the paging, with the segmentation, you can get as many segments as you like. Okay. But for the paging, the linear address space is just 1. So you have to manage your linear address space yourself with the paging. You have to say that I'm going to keep my programs at this position. I will keep my data at this position. I will keep my stack at this position, and etc. Okay. Remember, with the threading, multi-threading, if you implement your multi-threading in the user space, each thread should have its own stack. Who is going to manage those? You are going to manage it. With the segmentation, whenever there is a new thread, you ask the operating system to give you one more segment. Okay? And you are going to use that segment as the stack for that thread. It is as simple as this. And you don't care how large that segment gets, because operating system will handle the length of that segment. Okay? And of course this is possible. Can the total address space exceed the size of physical memory? Yes, because my program can have 10 segments, but I don't have to keep all of them in my memory, right? Can the procedures and data be distinguished and separately protected? With special kind of paging, yeah, but for segmentation, this is definitely yes. You could say that. Okay, this is a read-only segment. You cannot write to the segment, or you cannot execute it. This is a read and write, but no execution. You don't put any code in there. Okay, and for the shared libraries, if there is a DLL in there, of course this is a read-only segment. Okay, I can change these as I wish. Well, you might say that for the pages we have the same thing too, right? Remember the page table? We have, for each page, we have the privileges for read, write, execute, but that's not user tunable, right? Because user doesn't have any access to the page table. It is all tunable by the operating system. With the segmentation as an ordinary end user, I say that this segment is executable only. You can't write to it. Okay, so I can have these kind of distinctions. Okay, so procedures and data be distinguished and separately protected. Okay, and my segment sizes can fluctuate. They can become smaller or larger. I can't do the same thing with the paging, because with the paging you have one large address space, that's it. Okay, sharing of the procedures between the users facilitated. For the paging, if you use the position independent code, yeah, but for the segmentation this is so natural. Yes, I can do that, and I don't have to worry about the position independent code. Okay, so why was these techniques invented? Okay, for the paging, to get a large linear address space without having to buy more physical memory. Okay, for the segmentation, idea is the same, but on top of that, to allow programs and the data to be broken into logically independent address spaces, and sharing and protection by the user is the other plus. So this plus these three things is good for the segmentation. Good. So that's the segmentation. Again, there are lots of all the problems that you are having with the paging. Of course, you are going to have with the segmentation. Writing, this is swapping the segments out to the disk, loading them back in. Okay, segmentation faults, handling of those, MMU programming, and etc. They are all valid with segmentation, but I am not going to look at them. They are similar to paging. Maybe we should look at some practical system about this paging. Let's look at this paging and segmentation. Let's look at this system MULTICS. Remember MULTICS? It was developed in 1960s. It was actively used in 1970s, 80s, 90s, and 2000 actually, without changing anything actually. They run the same operating system, and you might say that the Windows has been running for the last 40 years, you might say, right? For the last maybe 30 years, yeah, from 1990s to 2020s. For the last 30 years, we are running Windows. No, Windows 11 has nothing to do with Windows 3. They are completely different systems. Their names are the same, okay? They are not the same operating systems. This MULTICS from 1970 to 2000, it was the same operating system, and it was running fine. Why did they stop? Why did they stop it then, running in 2001? Because the hardware that is running on, it just became obsolete, and nobody supported that hardware. It was very difficult to run that computer, so they had to shut it down. So very nicely designed operating system. The idea of MULTICS is, of course, is to provide computing services to homes and the businesses, like the electricity or the water or the gas. Okay, I am going to give you computing services to your home, and you are going to pay me a certain amount of money. That was the idea, and I am going to run the main server in using MULTICS at my central location, and you are going to connect to me using your terminals. Okay, so they had to invent lots of stuff, especially when they developed MULTICS. Actually, they developed its computer along with MULTICS too. So it influenced, for example, Unix is like the derivation from MULTICS. So it's kind of a simplified version of MULTICS. And the architecture of the Intel platforms are influenced by the MULTICS structure. TLBs and the cloud computing, they are all invented by MULTICS. Okay, so let's look at this idea of segmentation with paging from the MULTICS perspective. Okay, so the MULTICS virtual memory, maybe I should show you this one. Okay, so this is a typical segment descriptor for a MULTICS system. Segment descriptors are this. I have a table for segment descriptors. Okay. Inside these segment descriptors, I have information for segment number 0, segment number 1, segment number 2, and then 3, and etc. It goes that way. Okay. So the size of the segment descriptor is just 36 bits, and I have this, okay, segment descriptor for each process. Each process has this segment descriptor, and you can have as many segments as you like. Remember, for our compiler program, we had 5 segments or 4 segments, 5 segments, I guess. Okay. Let's look at each of these segment descriptors. Okay. So the first 18 bits is the main memory address of the page table. So this is segmentation with paging. Okay. Segmentation with paging. This one says that for this segment, I am going to segment this page. Okay. And its page table is at this address. So each segment here is paged. Previously, for the paging, pure paging, we paged the whole memory. This one is segmenting. This one is paging each segment. Okay, so this is the address of the page table, and this is the length of the segment in terms of pages. Okay, how many pages do I have in this segment? And then my page size can change depending on my segment. Okay, for some segments the page size is very small. For some segments the page size is large. For 1970, it's a very large segment size, 1 kilobyte. And if you don't like, you may use a pure contiguous memory for your segment if you don't like it to be paged. Okay, and then we have some miscellaneous bits here and some protection bits: read, write, execute. So each program will have this descriptor segment. Inside the descriptor segment, depending on the user needs, you have many segment descriptors, and each segment descriptor can point to a page table. Okay, so each segment is paged differently. Okay, that's how the MULTICS work. Okay, and this is the 34-bit MULTICS virtual address. First, you give the 18 bits as your segment number, and inside your segment you specify your page number, and inside your page you specify your offset. So previously for the paging we only use this part. So it is 2 to the 16, the total size of the maximum size of the page here, 2 to the 16. It's not very large, but again we are talking about 1970s. If you combine it with this, of course, segment numbers, okay, it's a how many bits is this? 36 bits, right? Is it correct? It's 34 bits, yeah. 2 to the 34 is the maximum addressable virtual memory for each process. Very large number for those days. Okay, so again, this is how you specify your segment number. So you can have at most 2 to the 18 segments. For inside each segment, you can have this many pages. Okay, and as I said before, okay, the segment number. Okay, inside the segment number, you get your when you do this conversion from the virtual address to the physical address. Okay, this is my virtual address, total of 34 bits. You get your first 18 bits. You make a lookup inside my segment descriptor table, You get your page table. From the page table, you find your page. From the page, you find your word. Okay? And this is done by the MMU during the runtime. Okay? During the runtime, it is done by the MMU. Of course, this is going to get slow, and this segment descriptors and the page tables are getting larger and larger. So they had to invent TLB, okay, kind of a hash table, kind of an associative memory, to help us do this in real time without going to the main memory. Okay. So they have to invent this. So this architecture is very influential. Okay, this architecture was very influential. Later, Intel architecture tried to do exactly the same thing, and they did that. And we have exactly the same architecture in the Intel platforms. If you like, your programs can have your segments, your page tables, and etc. If you like that. But as I said before, Windows stopped using the segmentation part of the Intel architecture. Nowadays, we are using only the paging features of the processors, not the segmentation. And by the way, this is the structure of the TLB, translation look ahead buffer. Inside my TLB, okay, you get the segment number and the page number. You look it up, segment number and the page number. If it is in there, and then you get your page frame, your physical page frame. Okay, so you look for this. You look for this page frame in your physical memory, and these are your protection stuff: read, write, execute. Like we did in Unix, read, write, execute. What is this age? Can anybody tell me what this age is?
It may be time duration that it exists in the TLBs.
Yeah, how long did I have this entry inside the TLB? That's one thing. Well, let's make it FIFO. We don't like the FIFO. Maybe this is the NFU with aging, right? So of course the older segments and the pages, they get old. Yeah, that's thing. But if I reference them after each clock interrupt, they get younger. Okay, so this way, if I'm going to replace one entry from this TLB, in this case it looks like the oldest one is this one. Let's replace this one. Nobody is referring to it. So the least recently used, or the not frequently used algorithm, not the frequently used with the aging algorithm, comes from the MULTICS actually. Okay, so this is the TLB structure, very very parallel to what I told you before about the TLBs and the page replacement algorithms. Okay, and Intel platform, as I said before, they tried to do the same thing. Okay, segmentation with paging. I am not going to talk much about it. Maybe I should just give you one 32-bit. Well, no. Well, I'm not. No. Well, I'm not. Since we are not using this architecture now, but idea is the same. So the idea is this: like, these are the segments, these are the pages, and these are the offsets. It's a 32-bit address thing, 32-bit computer. Segmentation with paging works with the Intel architecture. Even today, it is being supported, but our operating systems don't support it. That's what I'm going to say about the Intel platform and the segmentation. Okay, good. That will be the end of this chapter, chapter number 3, memory. Are there any questions? Are there any questions about? Where is it? Okay. If there are no questions, then I will start talking about the next chapter, chapter number 4. It is the file system. Okay. So far, Okay, maybe I should show you this. So far we have looked at these concepts in this course. We abstracted away the concept of processor, okay, and we used the abstraction of the process. Okay, we said that a process can represent a processor, or the thread can represent a processor, and keep the idea of the processor in mind. And doesn't matter how many CPUs we have in our system, we talk about the processes and we talk about the process scheduling, etc. So we spend lots of time about it. So that was the first abstraction. In our case, this was the abstraction about the CPU. Then when we came to the memory, okay, we started talking about address spaces, virtual address spaces. For the paging, it's a very large linear space of addresses. For the segmentation, many different linear address spaces, but the address spaces were the main abstraction mechanism. Now, when we come to the file systems, the file is going to be our new abstraction. Okay, what's a file? Okay, file is a place in our secondary storage to keep permanent data. Because for our computers, okay, we need to store large amounts of information someplace. That will not be possible with our main memory, because our main memory is limited. It's not very large, okay? And worse than that, when we power off our computer, that data goes away, okay? So we need to store our data in a place that will not go away, go away when the power is off. And we need to store this data in a way that many processes can share and modify and read the same data. So we are going to invent this new abstraction. It's called file. Okay. Once you create this abstraction mechanism file, then we can talk about this file systems. And the idea is very similar to memory, actually. I mean, inside maybe the segmentation, we divide our memory into segments, small segments, and the user makes that decision. And the file is the same thing. We divide our secondary storage into files. Each file starts from address number 00 to some large number. It's a linear space, and I can do whatever I want with those files. But the number of segments we talk about is, maybe we are talking about at most thousands. With the files, the number of files that you can keep on your disk is, we are talking about millions. Okay, so we need ways of organizing this data. What was our solution if our computer crashed previously? Okay, when we are doing the process scheduling, if for some reason, or when we are doing the paging, if our computer crashes, what do? We restart it, and we can't do anything, right? All the data is lost. But when your system is running, when the system crashes, you don't throw out all of your data from hard drive, right? You try to save them. So we have these kind of new problems now. How do we make our file systems resilient, more robust against these kind of crashes, unwanted effects? These kind of things will be our main issues on file systems. So file is our new friend now. Processes are the spaces now, the files. Once you know, okay, if you really understand these three concepts, processes, address spaces, and files, then we can say that you are becoming an expert operating system designer or user. Okay, so we are going to spend a few weeks about these file systems. Any questions? Okay, then that will be it. I'll see you next week.